was that?
So, our second speaker of the morning is Kelian Haring. We'll talk about S-matrix bootstrap and black hole collection.
Good morning, everyone. So, first of all, I would like to thank the organizer for the invitation and giving me the opportunity to speak here. So, this talk will go well after Leonardo's nice review. And I will continue this idea of S-matrix bootstrap and try to include into the game black hole production. So the main topic of this workshop is to understand better notable symmetries in gravity. And what I would like to ask today, the question is, can we tackle this question using the bootstrap? And maybe more precisely, I would like to see if there is a case or a specific setup when the bootstrap should provide a definitive answer. And right away, I will start with a disclaimer. So this talk is not based on specific paper or definitive results. So I will not have a definite answer by the end of the talk, but I will present some set of ideas and attempts and tools where the bootstrap could eventually provide help to answer this question. And so I really hope that it will trigger some discussions, and maybe we'll have make some steps towards the goal by the end of the week. So I had a simple slide on the S-matrix and S-matrix bootstrap that Leonardo already presented beautifully before. So we'll focus on the 2-to-2 scattering amplitude, the scattering of particles A and B to C, D. And in contrast to Leonardo, we use the letter T for the momentum transfer and not U. So I hope it will not confuse you. And so in the bootstrap, we have three main axioms or constraints. The first one is identity, the second is crossing, and unitarity, which is in the statement that priority is constrained. And we usually write an ACU for identity, crossing, and unitarity. So in formulating the conjecture of no-global symmetry, a black hole plays an important role. And so the philosophy I would like to pursue in this talk is try to input black hole production into the bootstrap and see what comes out. And so we supplement the standard bootstrap axiom by black hole production. So with that, I will start with a brief agenda of my presentation. So I will start by reviewing what is the expected implication of black hole production in a scattering amplitude. Now we look at two cases. The first is a symmetry-breaking amplitude, and the third one is an elastic amplitude. And then I will stick to the elastic case and look at what is the leading contribution of black hole production to the elastic amplitude, and then look at an example of a symmetry-breaking observable in that is a shift symmetry observable. So I write a sum rule for a shift symmetry observable and see what is the impact of black hole production to this observable. So what is the general idea of having black hole production in the scattering amplitude? The general idea is that if I look at the semi-classical picture and a scattered particle at high enough energy and small enough impact parameter, then you form a black hole with probability 1. And so small enough impact parameter is what? Is less than short radius, and to remind you its formula that depends on the center of mass energy S. Then the idea is that I form a black hole, I have a exponential number of black hole states in these energy windows, where the black hole entropy is given here in terms of the energy and blank. And so the probability of having an exclusive process, so like a 2-to-2 process, is exponentially small. And so we enter in this black disk regime, which is namely this partial wave combination, Sj is vanishingly small. And here I use the semi-classical relation between the spin and the impact parameter, which is simply given by the spin is the impact parameter times energy over 2. Okay, so now let's go into the symmetry-breaking amplitude. So let's start by considering an amplitude scattering of scalars A, B, C, D, when they're all protected by a global symmetry. And so at any level in perturbation theory, well, the amplitude is equal to 0. But now, let's assume that at some sufficiently large energy, some black hole threshold, will form a black hole with probability 1 with the same semi-class picture that we have before. So it's also for spin method, since black is spin, which is proportional to the structural values times the energy. And so the fact that we form a black hole with probability 1 simply the statement that the overlap when I sum over all black hole macro state is 1. So what is the solution to that? It's simply that this overlap is exponentially small plus some pseudo-random phase that depend on the black hole macro states and the external particle A and B. Very good. So now we can compute the discontinuity of the amplitude, which is given by unitarity by summing over intermittent states. And so we simply have the discontinuity of the amplitude is given by this sum, when here we have all the black hole microstates at fixed energy. And so it simply leads to the fact that the discontinuity amplitude is exponentially suppressed. Okay? So this is probably what we expect from black hole production, to have a discontinuity exponentially suppressed. But let's see naively what is the impact on observables. So with dispersion relation, as Leonardo mentioned before, so this is schematic. If we put dispersion relation, well, straightforwardly imply, if I plug this behavior, that the Wilson coefficient are exponentially small. Yeah?
So there is some assumption of typical microstates to have this e to the minus s, the leading term. When you wrote that solution to this
Here? Yeah.
Here, right, when you wrote this solution to the minus s.
Yeah, that they all typically. That when I form a black hole, I will. I have an equal chance of creating two particles than other two. Yeah, that's. Yes. Yeah. Because.
You say the solution is a solution?
Yeah, solution is.
A solution.
Maybe it's better.
A typical solution.
Typical solution, exactly. That's maybe a better word. I agree. Okay.
I have a question about this last formula.
Yeah.
You write that the Wilson coefficient size goes as something that depends on the black hole entropy,
Yeah.
but the Wilson coefficient is something that is theory, a property of the theory, but the black hole entropy is particular to the particular black hole. So which black hole are we supposed to put for this
So
black
that's,
hole?
so the typical. That's just the entropy of a black hole that I used the formula before. That's.
It depends on the scale of the process, you're saying, or
It's just the size of the smallest black hole that you can form.
smallest black
Yeah,
hole.
yeah.
Okay, good.
Okay, but this picture is schematic here, and it's really hard to make it precise because first of all, here it's not an elastic process, so discontinuity of the amplitude is not positive definite, so we can have lots of cancellations, and yeah.
I'm a little confused by the term Wilson coefficient here. You're describing an S matrix in Minkowski space.
Yeah, so the Wilson coefficient is the observable that Leonardo defined before. So if I write the amplitude as an expansion in terms at low energy, in terms of Mandelstam variables,
Yeah.
is what appears in front of these Mandelstam variables.
Okay, so you're using the dispersion relation.
Yeah, that's the dispersion relation, yes. Thank you for the question.
Your sum of the pseudo-random phases might actually vanish, right?
Yeah.
Depending on how pseudo,
So this just-
how pseudo it is.
Yeah, exactly. This
So,
is
is that going to change any, if it does vanish, like, your typical Gauss sum would vanish.
it's even smaller. Yeah.
And so is that, how does that change? So that would be stricter bounds on these Wilson coefficients? I guess so.
Probably would be even smaller. Yeah. But it's so this picture is really it's really rough and it's really hard to make it precise. And it's why I'd like to now move on to maybe a more clear amplitude, which is the elastic case. So now let's consider 2-to-2 scattering of a non-identical scalar, but now in an elastic process. So we'll take the scattering of particle A and B to A and B, and the leading contribution to this process is this famous T-channel graviton pole exchange. And now this amplitude is really nicer because it has much more control in its computation than the symmetry breaking, because it has all the issue that we discussed just before. Especially now the discontinuity on the amplitude in this channel is positive definite from inequality. Yeah.
Sorry, even in the inelastic case, you could have used the generalized optical theorem, right? That tells you that the discontinuity for AB goes to CD can be written as a sum of an outer product of matrices.
Yeah.
You know, AB goes to X times
Yes.
X goes to CD, and that would give you lots of nice positivity properties that reduce to this.
That
in the
will
inelastic
give you,
case.
but now you have a matrix amplitude and you need to deal with it. And so,
Right. But there are tools for.
Yeah, there are tools. But in particular, one of these amplitudes in this matrix will be this elastic one, right?
Yeah, exactly.
But I would like to emphasize that even though we now talk about elastic amplitude, we also have a blackness regime. And for that, I would like to review this nice ACV picture by Amati, Ciaffolli, and Veneziano, starting from late 80s, which looks at the scattering amplitude in an energy impact parameter space. And so it has various regimes. So Leonardo already mentioned it before. So we have the Born regime, which simply, if I look at really high impact parameter, a fixed scattering energy. Well, the only thing that happens is that will exchange one gravitons, and so will be dominated by this Born regime, and the amplitude will be elastic. Then we have this agonal phase, which control the amplitude at large energy fixed momentum transfer. And finally, if we go to large energy and fixed impact parameter, we enter this black disk regime, which starts at the radius of the black hole. Okay? And in this case, the amplitude is completely inelastic, or maybe exponentially small, but let's first assume that it's completely inelastic. Finally, if I go at small impact parameter, small distance, well, I will enter a string regime. And here we know how to do computation in string theory. And for example, trivial string theory is somewhat.
Sorry,
Yeah.
So in this plug, in between I-kernel and black hole, there should be a regime where it's gravitational radiation.
Yeah, and here you have inelasticity that kicks in. So you have a tidal effect, gravity wave, but I didn't put it
In principle, perhaps before you form a black hole, the S matrix
Yeah,
already
many other effects, yeah,
close
yeah.
to zero.
Yeah. It could be, exactly, yes. But here I really wanted to focus for this, from the different zoom on this region of this plane. Yeah, you have more lines in this graph. Very good. So, Leonardo already mentioned before, but we have more control for the SI amplitude, especially the radial limit. We have two subtraction at fixed terms of t. And now if we go to the smear amplitude that they also defined, when define this class of smearing by the behavior close to the two endpoints. And so the intuition behind this smearing is that you focus at small impact parameters, so at fixed b, but then you have a polynomial tail. And so now if I focus with a good enough function, well, I will suppress this exponential tail. And so the only thing that remains is fixed spin, and so the amplitude will grow linearly at most. And so the question is, can we compute this coefficient here? And so that we can do if we assume black hole production. And so what happens is that if I zoom enough on this with this smearing function, I will focus on fixed impact parameters. So the only region that can contribute is spin at its order of energy. I can produce this linear contribution, but this corresponds really to fixed impact parameter. So now we're really in this black hole regime. So this is the first time that black hole production can enter. And so we can actually compute this coefficient, and using complete miscorrelation of Legendre is simply 0. So it means that using smearing plus black hole production, I get the amplitude is one subtraction and not two subtractions. So that's the first time that black hole production enter. We get something stronger in quantum gravity that simply increases. Now, standard tool is with dispersion relation, so that's already reviewed before. So it's simply the EFT with unknown physics and the bridges, so the EUV. And this is a standard relation that you may have seen if you studied raw equation for pi scattering. So let's now look at the as the black disk regime for this elastic amplitude. So again, in this case, we have Sj is 0 for if I'm less than this black disk spin and above some black hole threshold. And now if I use that Sj is 1 plus I times the imaginary part of the connected part of the amplitude, well, it simply gives me that the connected part of the amplitude is fully imaginary, it's just equal to I. And so this I wanted to contrast with the inelastic case. For example, the symmetry-breaking amplitude, where here, because I don't have the connected part of the amplitude, I have that the partial amplitude is vanishingly small. But here is actually I. Okay? So what does it imply that it's I? So when I take a dispersion relation, it simply relates the amplitude with the imaginary part of the amplitude in UV, so for example in this regime. So I can compute the leading black disk contribution to the amplitude using dispersion relation. So I can simply take my dispersion relation that I had before and plot for the discontinuity of the amplitude this black disk ansatz, which is simply plotting that the imaginary part of the amplitude is equal to 1. And so you can do the computation exactly. And what you get is this term. So it's proportional to G Newton squared. It's non-analytic. So for example, in even dimension, it's a log. And it's log t. And it's G Newton squared. So it looks like a one-loop contribution to the amplitude. So this relates black hole production to some part the one-loop contribution to the amplitude. So really, it's a non-trivial relation between UV and IR. So after that, I would like to see what more can I do by plugging this contribution from black disk into its spectral relation. And so the first example I would like to take is a complex scalar coupled to gravity, and see what will affect the Wilson coefficient of this black disk amplitude. So, yeah.
Could I ask a quick question?
Yeah, sure.
So, in what you've been doing so far, you've been treating black holes as if they were stable asymptotic states?
No, they're intermittent states.
So is there, does the lifetime of the black hole enter in any way in the...
No, not in my computation. No.
There's no like corrections because of the lifetime?
So it's like...
Like at some point, if you make it a resonance which is very broad, right? Then I guess you sum over it in the same way.
The only thing I'm using is that I will form a black hole. It will live for potentially a long time, and then it will emit some Hawking quanta. And so the chance that I have the same Hawking quanta that I want at the end is suppressed.
I don't think the limit that the entropy is big.
Right.
So
No, I understand. I'm asking if there's a way to estimate corrections to that limit.
That would be really interesting, but I don't know. Yeah. And here, for example, here I only use the fact that it's close to 0. I didn't use that exponentially small, right, so far, in this elastic case.
So basically what you're doing in this elastic amplitude is that the extra piece has to cancel the tree level piece, so you get basically 0. Is that what I correctly interpreted it?
Here?
Maybe back up a little bit. Or you have this 1 plus IA, right?
Yeah.
Right, and then maybe I've been lost. You have this tree level gravitonic exchange, right? This is corresponding.
Yeah, so tree level gravitonic exchange.
Because that's there in the elastic amplitude and not in the inelastic amplitude. That's why I was.
Oh, this one, you mean?
Yes, the one.
It's just because it's just the fact that I can have nothing happening, just the connected part.
Oh, just the connected.
Yeah. Just without this. But if I have an inelastic amplitude, well, I can have just lines. Yeah. That's a key difference.
The sense of this being a black hole effect is you're saying it cancels the connected part, so that nothing comes
Yeah, here it's just that in this, so a black hole implies this. And so now if I look at this relation, it implies that this part has to be purely imaginary. But now if I don't have a connected part, well, I don't have the one, and so it means that this has to be vanishing small. That's what I'm using, nothing more.
Sorry, do you have any idea of approximately what is the red trajectory around j equals 1? I mean, usually, for example, if we don't have a black hole, the red trajectory should be roughly like 2 plus alpha prime t, right?
Yes.
What's in this case if we have a black hole? It's 1 plus something?
So in a non-perturbative amplitude, the UV, you mean the UV behavior?
Yeah.
So the UV behavior is given by, so I fix t.
Yeah.
I fix t, the UV behavior is dominated by actually this regime,
Yes.
the Economic regime. So it's well controlled by the trivial phase shift. And so the black hole regime doesn't matter in this region.
I see.
Yeah, it's the part that is inelastic. It's which could be eventually non-universal, and does not contribute to the radial limit of the amplitude. Radial limit really is controlled by this econal phase, and especially by the trivial economic phase, and so influence it. Yes. It's why in the paper with Sasha we really carefully explored all this region, and really it was from this region that. Okay. So if there is no more questions, let me go to this example of a couple of scalar coupled to gravity. So let me write an action of a complex scalar with the standard Einstein term, the Maxwell term, and then an EFT expansion for complex scalar. And so I would like to focus on this G1 piece. So this G1 piece, if we have a shift symmetry, so phi equal to phi plus constant, this has to be 0. And so one question, so one maybe first step in understanding no global symmetry in gravity, is trying to understand if gravity forbids having G1 equal to 0. So can we show that G1 has to be strictly bigger than some value delta? And so if you look at the amplitude, so that's the diagram that contributes to the amplitude. And so at low energy, we have the Einstein contribution, the channel exchange. We have the Maxwell piece. And then we have this G1 that multiply energy squared, so random S. And so the first thing I want to say is that in quantum field theory, G1 is not dispersive. So as Leonard reviewed, the first time the dispersive is the G2, which multiply S squared. But now the G1 multiply S, so it's not dispersive in the theory with without gravity. But with gravity and using black hole production, I argued before that actually one subtracted dispersion relation is also allowed. And so we can write a dispersion relation for this G1. So it's what I did here. So on the left-hand side, we have the T-channel exchange due to electromagnetic, the photon exchange. Then we have the G1 and something else, or the T. But now if you look at the right-hand side, well, we have the discontinuity of the scalars, the phi going to phi. We also of the U channel, which is phi star going to phi star. So both of them are positive definite, but you have a minus sign. So of course the combination is not positive definite. And that I would like to contrast with, for example, if I look at the G2, so I think the same notation that Leonardo used before. So this one has a plus in between. So it's the one that is famously positive using causality argument and is modified due to gravity, so I can have a time advance to the Shapiro time delay. And the G4, for example, I can take the forward limit and also have a plus, and this one is strictly positive. So here, as Leonardo also did, I ignored the EFT loops, and that's a question you can come back later if we should take into account EFT loops. So now, let's look at contribution of the black disk to this Wilson coefficient. So I can split my discontinuity into the discontinuity of the amplitude and extract the black disk regime out of it. And with a black disk, I just use the imaginary part of the amplitude to be 1. And so this continuous black disk can be simply written in this formula in impact parameter space. When here I integrate in D up to the Schwarzschild radius, and it's valid for some energy larger than some black hole threshold. And so now if we go, for example, in the forward limit, and I compute this integral, well, I get something that is suppressed between the black hole threshold and mass Planck, and is given using the black hole threshold. So now, for example, if I plug that in this special relation for G4, we had before, which was strictly positive, I could take the forward limit, well, we see that G4 has to be positive and bigger than something that depend on the size of the smallest black hole.
So can I have a question? I'm a bit confused. If you consider the single subtraction dispersion relation, you get G1 that is not related to G Newton. There's no G Newton in that dispersion relation, right?
No.
So it means that you can just shut down G Newton and still get some constraints on the
Yes.
Then how can it be related to the gravity if you can shut down?
The only way I can shut down G Newton, the only way I can't shut down G Newton because I need G Newton to have black hole production.
Yeah.
And so that's how it enters.
Yeah, but if you just look at the dispersion, single subtraction dispersion relation without assuming UV.
It doesn't seem to have G Newton. But that will be interesting to see what happens. Okay, thank you for the questions. So now let's look at G1. Let's go back to G1. Well, we have a minus sign, so we cannot conclude anything. But maybe not surprising because we don't expect the Wilson coefficient at a broken due to gravity effect to be polynomial in the black hole size, but more exponentially suppressed. And so maybe it's not a surprise, but it has to be the case. So to see this effect, maybe let me do a more refined black hole ansatz, because so far I only use the partial amplitude is vanishingly small. So let me put back the fact that it's exponentially suppressed. And so what it means that now the imaginary part is not just 1, but it's 1 minus a function that may depend on the external states and the energy and the spin times this suppression due to black hole entropy. And so now I can plug back into this partial relation, look at the contribution to G1, and I see that the 1 cancels, but now I have some dependence on this function that remains, and it seems to indicate that this G1 has to be of order that we saw above. And so one question I would like to ask is, okay, this function seems to be highly non-trivial and difficult to grasp and evaluate, but can we learn something about it? And maybe more about the difference. Can we evaluate this difference? And well, this is something maybe we can discuss later during the week. So that ends my discussion on this shift symmetry observable. So it seems that black hole production leads to this behavior on the coupling. And now we'd like to go to another example, which is a graviton MHV scattering amplitude. Yes?
Sorry, maybe this is a silly question, but so this term you wrote that you said violated the symmetry. Couldn't I in principle view it as sort of a correction to the metric on moduli space and then say that there might still be a symmetry? It's just the symmetry changed a bit. Like for like the pions, right? There are terms like this, but we don't say they break the symmetry. It's just as a symmetry is, there's a non-trivial metric for the moduli space.
I haven't thought about it.
Okay, yeah, I don't know. I think just from this Lagrangian, I can't tell.
I mean, you could also do a field redefinition, right? Like
What?
you could also do a field redefinition.
But
Yeah, but you could also
can't
generate
remove.
this, but yeah,
You could have started with just a flat metric.
a nonlinear field redefinition.
Yeah.
Yeah.
Oh,
Yeah, I mean,
yeah,
that's
this-
I guess that's kind of what happened with Python.
But I think the difference here is that any G term that he picks, he would get around.
Yeah, somehow you
that
need
wouldn't
more
be
terms
true.
to be able to tell that there's really no symmetry. I think.
It's a generic, it's a more generic thing than just saying that you correct these modules.
This one you can remove by equation of motion and fill out definition. It's always there. And
Yeah, but I mean, if you have a metric in the kinetic term, then this term will be there. And as long as that
could be.
metric has isometries, there will still be a global symmetry.
yes.
Okay, well, anyway, that's just
Yeah.
a comment. I don't know.
Maybe it would be good to understand that better. Yeah.
Before we move on, I just want to ask a question about dimension 6 sum rules, right? So this is a dimension 6 operator, and
Yeah.
as you point out, it's not this positive definite sum rule. But one thing one can do is expand the discontinuity minus discontinuity in partial waves, and whether the exchange states are dominated by scalars or higher spin states, you can get one sign or the other. Have you guys thought about that? I mean, because you're summing over essentially exchange black holes, right? So you could say something about what is the spin distribution and maybe get a better handle on the sign that way.
Yeah, I see what you mean. For exchange black hole, I wouldn't see how to evaluate which one is bigger.
Yeah, I mean, well, it's not immediately obvious, but you're making some kind of pseudo-randomness assumptions
Yeah.
about the black hole microstates. Maybe you could do something similar in the space of spins of black hole.
Maybe it's something to look into. Yeah, I agree.
Sorry, now I'm suddenly confused. Can you say why the lambda term doesn't violate the symmetry?
Also lambda, but lambda I cannot access. It's not dispersive. So
Okay. Okay.
yeah, the lambda I can access if I do non-perturbative bootstrap, but also not sign definite. And yeah, but yeah, lambda also. I focus on this G1 because it's dispersive and violates shift symmetry. And actually, if you go to high term, you can also do field definition to not have anything that breaks shift symmetry. So it's the only one I could try to access in this setup using simple positivity. Yeah, that's why I focused on this one. Yeah. Thank you for the question.
Maybe this was Daniel's question from before, but you could have a kinetic term with some apparent symmetry, right, which isn't a symmetry of the full theory. Right, there's plenty of examples like that in string theory, like type 2e string theory, where the moduli have an apparent SL2R symmetry, which is not a symmetry of the theory, but it's exact as far as the kinetic term is concerned. So I was wondering if you can hope to prove such a bound, because with maybe with supersymmetry, you can have a situation where the kinetic term respects the symmetry that's not there in the theory.
Yeah, maybe I don't. Maybe we should talk after. No, yeah, I haven't talked about this situation.
Sorry, have you tried using a primal bootstrap to bounce lambda?
I think it has never been done in the complex scalar case with gravity.
Yeah.
But without gravity, in a normal scalar case, it has been done.
Yeah, with gravity.
With gravity, no, it hasn't been done. That's something that would be interesting to do, but it hasn't been done. You could also do in high dimension, not 4, to have a higher divergences, but it hasn't been done. So let me mention this other example, which is similar to the previous one in spirit. So it's now imagery scattering amplitude in gravitons in V equals 4. So if we look at the imagery amplitude, which is in all informalies, it's the plus plus minus minus amplitude, and it's given by this kinematic prefactor times kinematic function, that is scalar. And so in the center mass frame, this spin prefactor is just f to the 4. And now we can look at this function. And we have the gravity Jingle exchange. We have the correction to two-point coupling, this is RQ. We have a graviton scalar exchange. And then we have all the rest of the Wilson coefficients. Now I would like to again focus on this term here, because this term breaks Z2 invariance for this phi. And so it also absent in linearly coupling gravity. But can we show that using dispersion relation that this guy has to be non-zero. So it's similar in spirit to the other one. We can write dispersion relation using superconvergent sum rule. And now it's also not sign definite. So the conclusion will remain as before. But maybe it's a nicer target because this beta phi square is a triple coupling square. And so it actually has to be sign definite. So maybe you can say something about the black hole exchange middle. I don't know. So I just want to mention that without black hole input, this has been bootstrapped in this paper last year, or 2 years ago now. And obviously this beta phi can be 0, but it's bounded from above, and the same for the triple coupling correction. Okay, so let me give a brief outlook and discussion. So here I try to discuss various effects of black hole production in observables. So it's really much work in progress and collection of ideas and has to be improved. And I'm really looking forward to many discussions we can have on this. And I try to motivate that it's maybe easier to work with elastic amplitude because we have more control, we have positivity of discontinuity, etc. One main question is, can we turn this expectation into precise models or precise conclusions? So turn this wiggly sign to equal sign. One of these questions is, I use this black hole threshold, so the size of smallest black hole, as an input. Can we understand what it is? I don't see how the bootstrap could try to answer what is the mass, what is the scale. So in this refined model, I use this function that depends on external states. So can we learn something about that, about the difference between the two, which was what appeared in the dispersion relation? So that's something I don't know if you can learn. It seems very complicated. One thing I would like to mention again is the importance of massless loops and full unitarity. So here I only use positivity and include black hole production, but we know that unitarity is more than that. It's actually the imaginary part is more than the absolute value squared of the amplitude. And for that, I just want to mention that in some case, it's actually some important. So intensity gravity in this work that Leonardo already mentioned, when I bootstrapped gravitons, SUSY gravitons in 10D. So this correction to Einstein gravity, which is this alpha times 3 to the 4. If you only use dispersion relation and only positivity, you quickly see that it has to be positive. And actually, using this primal bootstrap methods, you see that it's actually cannot be 0 if there is a gap between 0 and the minimal value. Next thing I will mention is that we actually need black hole production. To input this information, can it come from the bottom up? So it's highly non-trivial. Maybe we need to consider 2 to n amplitude, and this is not easy from the bootstrap perspective. And finally, maybe it's a more general question, is what is the easiest target for the bootstrap? So here I consider 2 examples. So this shift symmetry Wilson coefficient and the Z2, but maybe there is a better target. And finally, well, here I did only bootstrap in a flat space for the amplitude, but maybe there is something to be done in ADS-CFT, and I hope to learn more about that during the week. So with that, I thank you. And